Let us see some concrete example, forest fire simulation. Here we consider a very simple model. Again, consider a grid, and we assume that there is one tree at each grid point. We assume that the tree in the center of the forest starts burning. Then, for burning tree, each of its neighbor tree catches fire with probability p at every minute, like this. Here is one important point of simulation. We usually consider a random process which we would expect naturally in all situations of simulation. For example, here, it may be more realistic if we consider the fire moves to the next tree, not always, but by some chance. So in a simulation program, a computer flips a coin to determine whether the next tree catches a fire at every minute. Well, in the real situation, the fire spread would occur at every moment. Here, we simplify it to every minute. Then we assume that each tree burns out in B hours after it starts burning. Now, the question is when the forest burns out completely. Note that we have two parameters here, P for probability of spreading fire to the next tree, and B for the length of burning. If P is small, then the fire would stop because burning trees burn out before spreading fire. Similarly, if burning time, B, is too short, there is not so much chance to spread its fire to the next tree. So under which condition of P and B, we will end up burning out almost all trees in the forest? This is our question. Well, we may consider some other parameters such as the size of the forest and so on, but let's fix them and focus on P and B here. We may expect that both P and B need to be large enough. In fact, we can mathematically derive that the value of B times P determines the condition for the complete loss of the forest. In fact, by conducting simulations under this simple model, we can show some threshold constant C0 such that the forest is burned out if and only if B times P is greater than this C0. Of course, this is a random process, so even if B times P is larger than C0, there is some chance, say 1 out of 100 simulations, that the forest does remain partially. But this is a rare case. Note here that we can derive very sharp condition with a precise constant C0 by simulation. While it may be possible to derive a similar condition mathematically, the derivation of the precise constant may be difficult even under this very simple model. Well, simulation is something like this. Here is a simulation for investigating airflow dynamics in a bronchial tube of humans. Again, we considered digitization, which is now a three-dimensional grid, expressing a tube by a collection of cubes. Although it is not so easy and the formula gets complicated, it is still possible to express air movement from one cube to the next cube. But it may be very difficult or impossible to understand the global behavior analytically. Then, computer simulation is important to derive some law for predicting how a certain disease affects the airflow. We have seen how to design a simulation and how to use it. Then, this may be a good timing for me to mention the importance of supercomputers. A supercomputer is a computer that outperforms standard computers of each age, maybe 100 times to 10,000 times faster than a powerful PC of today. Supercomputers have been used quite a lot in simulations. Their supercomputation power plays a quite significant role in big simulations. In Japan, we are now preparing Fugaku supercomputer as a national project after K supercomputer. Of course, supercomputers are expensive. We often hear that a supercomputer can cost upwards of 100 billion yen for its development. Then you may wonder why they are so important. What good does a faster supercomputer bring? Well, let me illustrate what would happen when we have a 100 times faster machine. Consider this wind tunnel experiment. Let's say that for each experiment, it took you 1 hour to perform. Let's say you are going to change the parameters here and there and wish to conduct such experiments 10,000 times. Then that would amount to 10,000 times 1 hour, which is 400 days. However, if the supercomputer becomes 100 times faster, then you can shorten that experiment from 400 days to just 4 days. That is to say, what would have taken you over 1 year to conduct a wind tunnel experiment can now be complete in just 4 days. That means when you design a car, you will be able to try out many new designs over and over again. Or you could also contribute to improving the accuracy. For example, when we look at the grid here in a weather forecast, suppose again that with a 5 kilometer times 5 kilometer grid, you are able to compute it within a reasonable time. If the supercomputer becomes 100 times faster, you will be able to run the computation for a grid that is just 500 meter times 500 meter with the same amount of time. Thus, you can increase this accuracy. The precision or accuracy of the model can thus increase while spending the same amount of time. So if you think that simulations are important, you may be able to appreciate supercomputer power. Of course, here again, the algorithm design is important. Even if you have 100 times faster machine, it is waste of this computational power if you cannot make use of it. Excellent hardware and software are both important.